let's have a look at graphing skills. GCSE level, I see all sorts of terrible graphs, and we're just going to assume that you can graph things properly, but there's more than that. Graphs serve a purpose. We draw them for a reason, and that reason is to extract data. Now, in physics, we like straight line graphs. Everything we do in physics, in practicals, is going to be trying to get straight line graphs. And if a relationship isn't a linear relationship, we're going to modify things to make it so it is. Now, straight line equation, depending on where you live in the world, it will be one of these three, probably. Y equals mx plus c is what I'm going to use throughout this video. But if you live in a part of the world where they use a as the gradient and b as the intercept, or b as the intercept, try again, b as the gradient and a as the intercept, then just adjust what we're doing accordingly. This is what we use in the UK, so that's what I'm sticking with. So we're going to try and get our equations into the form y equals mx plus c. Now there are some very few equations where we are quite happy with curves and things. Maybe we're looking at sinusoidal relationships or something, but it's quite rare. Usually we're trying to get straight lines. But what I see when students plot graphs, even at the start of A-level, is things like this. You can zoom in if you like. For some reason we're plotting distance versus time. Don't know why, doesn't matter. We're plotting distance versus time. And the students put a false origin, except they haven't. They've broken the axis. Never do this. Never do these zigzaggy lines. You don't need it. They haven't bothered with the units on the axes. I've had to label that. And they've done this dot to dot with dots instead of x's and connecting lines. And it's just rubbish, because the data doesn't take up enough space at all on the paper. Now, what we want is it to space out the data. So we have to use false origins where we can, and we want to ideally have more than half the paper filled with data points vertically and horizontally. We can use gradients. We can measure gradients when we've got false origins, but we can't measure y-intercepts. So we have to then calculate the y-intercept by using y equals mx plus c. And as I've said there, never break the axes. So this is a better graph of the same thing, the same data. And you can see we've now got our false origin. This is good, little tick. There's no breaking the origin, no zigzaggy line. Data just about occupies the vertical space. The scale could have been extended out, I suspect. It just about occupies it. Maybe. Units are there. Units are after the slash, by the way, because we want our quantities to be dimensionless on the axes, because we are representing those quantities as lengths. We are representing this time spatially as a length. So to make sense of that, what we're going to do is we're going to divide by the unit of time so that what we're plotting is just a number. And then we're going to represent that as a length. And this is already a length, but we do the same thing anyway. Line of best fit is a straight line. And when we calculate the gradient, notice that I've drawn little circles on the line, not near the x's. I've tried to avoid the x's. I've written the coordinates of those points. You can draw lines with the ruler back to the axes if you want to. I've done the gradient calculation, including the units. That's great. That's what we want to see. Okay. And when I do the intercept calculation, I use this point up here, and the gradient I'd already calculated, because big values means less uncertainty, which we'll come to later. So when we do those gradient calculations, the triangle some people draw, but the points, the key thing is the points on your graph, as far away as they are, they need to be at least 8 centimeters away from each other vertically and horizontally. So that's important. Don't count the squares. Use the values from the x and y axes. Don't be counting squares. That's how you learn to do gradients in maths, but it's a terrible habit to get into. Don't count the squares. Not for gradients. We will for areas, but that comes later. And gradients have units. It's the unit of the y-axis divided by the unit of the x-axis. Gradients have units. So if we want to determine the y-intercept, as I've just said there, use large values of x and y and the value of m that you've just calculated. Don't use the data points, use the line. The data points have served their purpose once you've drawn that line. If you want areas, and there's some times where you're going to want areas, you've got a velocity time graph, for example, the area represents displacement. A second. If you want areas, you're going to have to count the squares. There are various other ways of calculating areas, but this is what we do in A-level. And then we multiply the value of a square by how many squares. And any part square counts as a half square. That's quite critical. Areas below the x-axis are negative. You can read that yourself. So here's a graph. This graph has distance on the y-axis, time on the x-axis, and for some unknown reason we're going to calculate the area of this. There's no physical significance of that. Don't know why we're going to do it, but let's do it anyway. Doesn't mean anything, but let's do it. So we're going to calculate the area. It's a curve. If it was a nice regular shape, we could use geometry to calculate an area, but because it's a curve, we're going to have to count the squares. So let's start with the big squares. We count the big squares there, and we know how many, there's 25 little squares in a big square, and so we've counted the big squares. Then what we can do is count the little squares that are whole squares, and I've written them on there so I don't lose track of them. And then finally I can try and count those little squares, those little squares that are all the way around the edge as half squares. And you can calculate the total number of squares, multiply it by the quantity represented by a single square, which in this case has no physical significance at all, units of mass, units of meter seconds, whatever that is, and there we go. We've got our area. So that's how we do areas. Fine. So how do we get equations into the form y equals mx plus c? Well, remember that y equals mx plus c is a variable equals a constant times a variable plus a constant. You plot y on the y-axis, x on the x-axis, because they change. It'd be really boring if they didn't. And m must be a constant if it's a straight line. So that tells you what's going on here. Variable equals constant times variable plus constant. So let's take a nice easy example of something we want to get in that form. F equals ma. That's kind of already in that form. That's variable equals constant times variable plus 0. So we expect a y-intercept of 0, and the gradient would be the mass. That's nice and convenient. If we plotted it this way round, so if acceleration is constant, then we have to switch the a and the m around. Not a big deal, but we've now got m as the variable and f as the variable. But if f is the constant, oh dear, we have to do this. Now that's still f equals ma, just divided through by m and written it in the form variable equals constant times variable, and this is plus 0. So I would plot a on the y-axis and 1 over m on the x-axis. Or, if f is a constant, I could have plotted the axes the other way round, actually. M on the y-axis and 1 over a on the x-axis. And the gradient would still equal that constant force. Let's pick a different equation. Let's pick c equals f lambda. If f is the constant, we're already in the form y equals mx plus c. Nice and easy. We plot c versus lambda, then that constant f can be determined by measuring the gradient. But if the wavelength is constant, then we have to plot c versus f, and the wavelength will be the gradient. Nice and easy. But if c is constant, then we have to plot f versus 1 over lambda, or lambda versus 1 over f, and c will be the constant, c will be the gradient. Well, that's fine, but so far none of these have had a y-intercept, so let's look at one with a y-intercept. Let's look at v squared equals u squared plus 2as. Okay, well, if acceleration and initial velocity are constant, we're kind of already in this form. Although I appear to have messed up my colours a little bit. There we go. S should be green to indicate that it is a variable. So we plot v squared on the y-axis, s on the x-axis. The gradient is 2a. So if we want to know what a is, it's going to be half the gradient. We're just doing algebra. Algebra over here. You want to know what u is? Well, u squared is the intercept, so u is the square root of the intercept. And you can rearrange these equations however you like. You know, we could look at s equals half at squared. No problem. Well, the y-intercept is 0. That's boring. No problem. But what if we had a y-intercept? Well, this is a bit more complicated now, because look, we've got variable equals constant times variable plus constant times variable if acceleration and initial velocity are constant. Ah, that's a problem. It's in the wrong form. So we're going to have to divide through by one of these variables to get rid of this constant times variable quantity. Well, given that this one the variable's t and this one the variable's t squared, t here, t squared here, it makes more sense just to divide through by t. If I divide through by t, I end up with variable equals constant times variable plus constant. So you can see I swapped these terms around as well, just to get in the form y equals mx plus c. It's complicated. It is complicated, but it's a skill that you will need to acquire. It gets more complicated when we have logarithms. So a equals a naught e to the power of minus lambda t. What if a naught and lambda are constants? Well, the basic rule here is to get these in the form y equals mx plus c, you take the natural log of everything. And if you do that, and using your laws of logs from before, you get this, and that's in the form y equals mx plus c. Let's just write it the other way round, swap these two around. Plot this on the y-axis equals constant times, plot that on the x-axis, plus constant. Well, minus lambda is the gradient, so lambda is minus the gradient. And natural log of a0 is the intercept, so a0 is going to be e to the power of the intercept. Remember that the natural log and e to the power are inverse functions. Natural log and a power are inverse functions. So that's fine, but we've taken something that would have been an exponential decay and turned it into a linear graph. Really, really helpful. Or we've got this, a equals c times x to the power of b. And we're told that b and c are constants. Well, I've got no idea what b is. What am I supposed to do to find what b is? Well, if I use my laws of logs, I log everything. Log base 10 of a on the left, log base 10 of the right hand side, but because they're multiplied we can split it. Remember those laws of logs from before. And so I've also switched around the positions of these, so I've got plotting this on the y-axis, plotting this on the x-axis, and I end up with b being the gradient and log base 10 of c being the intercept, so c becomes 10 to the power of the intercept. We've got our equation. It's a power law, and we've made it a straight line, so we can determine what the power is. Really useful skill. Or something like this. A equals c b to the power of x. And we're told that b and c are constants. Wow, how are we going to find what they are? Same thing we did before. We just log everything, and then we arrange it so we've got a variable equals constant times variable plus constant. And you've split that log up using those laws of logs. So it's complicated. Yes, it is complicated, but it's well within your capability to do it. So any linear relationship or any polynomial, you can just rearrange it, usually. If it's an exponential, you're going to have to do the natural log of one of the variables, or natural log of everything, actually, and then plot the natural log of one of the variables versus the other variable. And if it's a power law, you're going to plot the log of two variables. Trig functions, well, they're a little bit different. If you had a trig function like this, then you would have to plot y versus cosine of theta to get a straight line where a would be the gradient. But you would still be able to do that. So it's a little bit different, but it's the same idea. You're just trying to get a straight line by doing algebraic manipulation into the form y equals mx plus c. And if you want to practice that, which you should, go and have a look at these Isaac Physics questions, get cracking on some of them, see how you get on. And good luck to you.